Let's use our furniture production problem once more. As discussed in another video, the model shown here describes an optimization problem where we can produce tables, chairs and loungers out of a limited amount of smaller parts. We have used 2x2s, 2x4s and 2x6s. Now let's assume that we have developed a new technology that allows us to glue together a 2x2 and a 2x4 in order to produce a 2x6. Having this new technology, we can produce loungers consisting of two 2x2s and two 2x4s. That means that we can produce loungers in two different ways now. How can we model the production of tables, chairs and loungers in such a setting? Think about it and try to formulate a model by yourself. Pause the video now. A straightforward approach to model the situation is to consider the new lounger as a new type of furniture. We would use x1 for the number of tables, x2 for the number of chairs, x3 for the number of loungers made in the old way, and x4 for the number of loungers made using our new technology. The model would look like this then. We still maximize the revenue. 16 times the number of tables plus 10 times the number of chairs plus 9 times the old loungers plus 9 times the new loungers. Subject 2, we need two 2x4s for a table. We need one 2x4 for a chair. We need one 2x4 for the old lounger. And we need two 2x4s for the new lounger. The 2x2s, we need two of them for a table. We need two of them for a chair. We need one for the old lounger. And we need two for the new lounger. Only an old lounger needs the 2x6s. The domains. In case you found this model by yourself, pause the video again and spend some time to think about if you can come up with a different model. Pause the video now. An alternative way to model the situation is as follows. We use x1 for the number of tables. x2 for the number of chairs, and x3 for the number of loungers, no matter if it is a lounger made in the old way or a lounger made in the new way. The trick now is to define an additional decision variable, say y, that represents the number of 2x6s which result from a glue-up of a 2x2 and a 2x4. The objective is to maximize the revenue gained by selling tables, chairs, and loungers. With regard to the 2x4s, we need 2 for a table, 1 for a chair, and 1 for a lounger made in the old way. The availability is 6. And here's the trick. 6 minus the number of 2x4s that are used for a glue-up to make 2x6s. In a similar way, we can formulate the capacity constraint for the 2x2s. We need 2 for a table, 2 for a chair, and 1 for a lounger made in the old way. And the capacity limit, it's 8. 8 minus the number of those 2x2s which are used for a glue-up. So we have 8 minus y. The capacity constraint for the 2x6s reads as follows. We need 1 2x6 for a lounger. The availability is 4 plus the number of those which result from a glue-up. As always, we must not forget the domains. This model formulation might not be as easy to understand as the first model. To understand why this model works, it is helpful to figure out the maximum number of loungers that you can produce from the small parts that are given. Don't forget, a lounger can be made either in the old way or in the new way. So, if you produced no tables and no chairs, what is the maximum number of loungers that you could make? Have a look at the Lego bricks and find the answer. Pause the video now. Let's see. The right answer is 5. In mathematical terms, this feasible solution can be described by x1 equal to 0, x2 equal to 0, x3 equal to 5, and y equal to 1. I highly recommend that you check that this is indeed a feasible solution by checking that all the constraints are fulfilled for these values. Further insight can be gained by answering the following question. What is the maximum value for y such that a feasible solution still exists? In the real world, this is clear, because y is the number of glue-ups. We have 6 2x4s and 8 2x2s. Therefore, it's obvious that at most 6 glue-ups can be done. We can derive this from the model by looking at the left-hand side of the first two constraints. All x's are greater than or equal to 0. Consequently, the smallest value of the left-hand sides is 0. This means we have that 6 minus y is greater than or equal to 0, and 8 minus y is greater than or equal to 0. Therefore, y cannot be greater than 6. Y equals 6 and all x's equal 0 is a feasible solution, as you can easily check. Note, this reasoning is based on the fact that constraints and domains interact. This is very typical. When you try to find out how and why your model works, you should carefully check how different parts of the model interact. Models are often more tricky than you first think. So when you try to understand a model, or even better, if you try to formulate a model by your own, always have such interactions in mind. To summarize, what is the lesson that we should learn from this video? We have seen two different model formulations for a furniture production problem. The first one was quite straightforward. The second one was slightly more tricky. Both models are correct. Both of them describe our problem. At this point, we have no reasons to claim that one model is better than the other. By presenting these two models to you, I'm trying to emphasize that there is not the model for a problem. The saying many roads lead to Rome is in particular true when it comes to modeling. Often, the choice of decision variables has a huge impact on how a model functions. My advice to you is to try out different ideas. Sometimes a straightforward set of decision variables is okay and leads to success. But sometimes a not so obvious idea is needed. This is what makes modeling so hard for beginners. There is no recipe that enables you to formulate a correct model for any problem. It all boils down to experience. Try to formulate models by yourself. Try to find alternative models in cases you already know a model. Once you have a model, modify your problem slightly, like introducing a new way to make lounges in our example, and try to formulate a model for this modified problem. And most importantly, do not give up. Whenever you make a mistake and you understand why this is a mistake, you have made a step forward.